So in this video we're going to go over two theorems that are used later in proofs mostly, but they do have some applications to our work with maximums and minimums. So the first is called Rolle's theorem and the second one is called the mean value theorem. So Rolle's theorem gives you a condition on where you might be able to find a critical number. So it says if your f is continuous on a closed interval a to b and differentiable on the open interval a to b. So continuous means you can draw it without picking up your pen. Differentiable means that it's smooth but also continuous. So if f of a equals f of b, so what that means is that if the y values are the same at the end point, so same y values at the end points of your interval, then there is at least one number c in between a and b so that your first derivative is 0. So if you have two function values that are the same, so we can think of that like this. So here's our number line, this is a, this is b, then there has to be a place in between there where the derivative is 0, so long as your function is smooth and continuous. So you can try drawing it so that it doesn't happen, and it can't happen. So the first thing is you could just draw your function like that. And then there's lots of places where the slope is 0. So that doesn't work, so let's go ahead and erase that. You could also draw it so that your function went like that. Well, then there's definitely a place where the slope is 0. You could draw it so that your function went down. Well, there's definitely a place where the slope is 0. So if we kind of think through all the cases, it's pretty much impossible to be continuous and smooth and not have a derivative of 0. So this is saying you're going to have one of those nice critical numbers in between this a value and this b value. So if we look at some examples below, we're going to talk about the places where Rolle's theorem does apply and then the places where it doesn't. So in this example, my f of a equals my f of b, so my endpoints are the same, and my function is smooth and continuous, and there is a place in between where my f prime of c equals 0. So remember, having a critical number doesn't guarantee a maximum or a minimum, but in this case it actually is. Rolle's theorem would not apply to this function because even though the endpoints are the same, f of a equals f of b, my function is not differentiable there. So there is a relative maximum there, but it is not one that's guaranteed by Rolle's theorem. So Rolle's theorem wouldn't say that. Rolle's theorem says there's a place where the derivative is 0, and there's definitely not a place where the derivative is 0 there. In fact, f prime of c is undefined at that place. Okay, now if you take away the continuity, then Rolle's theorem doesn't work at all. So here we have a function. Let's go ahead and say that this is a and this is b, and we have f of a equaling f of b, but there is no place where f prime of c equals 0 in the interval a to b, and that's because the function's not continuous. So even though my endpoints are the same, Rolle's theorem doesn't apply there. So Rolle's theorem is pretty limited. It only applies when you have a continuous function, so continuous, and it also needs to be differentiable, so smooth and continuous. You also need the endpoints to equal each other. So the easiest place we can do this is the x-intercepts. So if we have two x-intercepts of a function, then somewhere in between the derivative has to be 0. So example 1, we're going to use the two x-intercepts of this function f of x to show that f prime of c equals 0 for some c between the two intercepts. So the first thing that we need to check is continuity. So for continuity, the first function that is part of this is a polynomial, which is continuous. The square root is continuous as long as the x is within its domain. So this function is continuous as long as x plus 1 is greater than or equal to 0, which means everything from -1 to infinity. So we need to find two function values that are equal to each other, and it says to use the x-intercepts. So the x-intercepts are at when -3x equals 0, so x equals 0, and when radical of x plus 1 equals 0, so x equals -1. So f of 0 is 0, and f of -1 is also 0. So since f of 0 equals f of -1, there exists a c value that's between 0 and -1, so that actually needs to go the other way. So a c value between -1 and 0, where f prime of c equals 0 by Rolle's theorem. Now notice Rolle's theorem doesn't tell us where that place happens, it just tells us that it does happen. So we're going to check in Desmos to see if this makes sense. Okay, so let's start by typing in our function, and we'll use function notation so that we can also do the derivative command. So -3x square root x plus 1. And we can pretty clearly see that that does have x-intercepts where we said -1, 0. And we can also see that there's a place right here up at the top where the derivative is 0. And just to double check, remember Rolle's theorem doesn't tell us where it is, just that it is. So if I do f prime of x, I can see right here that this place, -0.667 or -2/3, is the same x value where my derivative was 0. Okay, in the last example, we are determining if Rolle's theorem can be applied on the interval -2 to 2 for this function. So remember, our very first thing on almost all of our theorems is to check continuity. So when we're checking continuity, we would be looking for, is there any place where the denominator equals 0? And in fact, there is. X equals 1. In fact, our domain is that x can't equal 1. And since 1 is in this interval, so since 1 is an element of -2 to 2, Rolle's theorem does not apply. Since f is not continuous on the stated interval. So those ones are easy. You just go, nope, can't do it. Rolle's theorem does not apply.